Hi, everyone. Good evening. Thanks a lot for joining. My name is Poojan, and I'm here for free pizza. Anyone else for that? No, we are here for learning. So yeah, I welcome you all of you on behalf of the K8SUG community. And I really appreciate you guys spending this time in this cold weather and joining us in person. But we have some attendees online. I'm just waiting for that confirmation. All right. Yeah, today it was an election. So yeah, really appreciate you guys joining. We have 2 sessions today, but before that, I'll just go through some of the promotional stuff, some discounts we have of Kubernetes and the certifications around Linux Foundation. So there we go. Yeah. One more detail to add. We are running globally and we recently launched this chapter in India. And to my surprise, we had more than 300 attendees in person. So I think they are a big competitor now for us. So, but yeah, still this turnout is also really, really appreciable. Thanks to our sponsors, AWS, for this beautiful venue. And let's take care about the hygiene of this place. And if you're returning, please make sure you take your belongings with you. Upcoming events, today is 27, and we have some really good events going on in Australia, UK, Singapore, and again in India. Coming with the discounts, I'll keep a couple of seconds for this slides. You might get more discounts on certifications of Linux Foundation using these QR codes. And after the event, we will post these on the Meetup as well for your reference, but you might want to focus on this coupons. Another discount, KubeCon London, is happening in the UK, and you could use 20% discount if you're attending using the promo code on the screen. Next up, if you'd like to join us as a volunteer, as a speaker, I'm so sorry. As a speaker, as a volunteer, please feel free to scan the QR code. And if you have any feedbacks, how we do events, if you have any more improvements, we are all ears. And that brings me to today's presentation. Really good topics about EKS Auto Mode from AWS team Matthew. And then we have talk about Kubernetes operators from Yashwardhan. So without any further ado, I would like to invite Matthew from AWS and proceed further.
So as solution architect, I really focus on all the container services inside AWS. Right?
Sorry?
You can take one more mic.
Oh, there's a mic.
EKS or Elastic Container Service, as well as Amazon Elastic Container Service or ECS, and a couple of others. There's somebody from IBM, for example, the Rosa offering, which is the Red Hat OpenShift on AWS as well. So if you have any questions after, we'll focus on EKS tonight, but after the fact, if you have any question, I'm happy to take them. Are we coming up?
I mean, I'm sharing.
You need to connect. Oh, you need to connect this for.
Yeah.
So for once, the people online see it before you.
All right.
Yeah, the online.
Okay. Does this work? Okay. I don't have experience speaking through microphone, guys. So what is happening?
I'll just move the.
Yeah. Oh, the other is fine. Okay, thank you. Yeah, bear with me on that. I don't have experience talking through microphone. It feels extremely weird. But yeah, I'm Vignesh. I'm a solutions architect at AWS. I work with Matt. Today, I'm gonna dive a bit deeper, more on the theoretical topic. Maths would be a little more interesting because it's a live demo. I'm gonna give you the technical overview of what EKS Auto Mode is, what it does, followed by Matt showing a live demo of the feature in itself. So, Amazon Elastic Kubernetes Service. 7 years ago, we launched this service. This was in response to our customers saying, building and managing production scale Kubernetes clusters is hard. It's time consuming. It increases operational overhead. They were building and monitoring and managing EKS control plane and securing it to provide the required level of resiliency and security. Amazon EKS did the heavy lifting in terms of managing the EKS control plane. And what this did for our customers was it gave back the time for them to focus on things that matter for their business in terms of innovation, in terms of working on tasks, in terms of building new features. So that is what essentially Amazon EKS was in a nutshell. And over the years, we've been innovating, building new features, hitting new scale milestones, creating new open source project, one popular open source project being Carpenter, and it's widely adopted in the industry as well. So yeah, over the years.
Anybody in the room use Carpenter?
Yeah. Yeah, I already said.
All right.
Nice. So that's a popular open source project. And for the year 2024, Auto Mode, this was launched or released in reInvent 2024. And annually, EKS powers tens of millions of clusters right now. So that's the scale at which we operate. At AWS, we listen to our customer feedbacks to inform our product roadmap. So when we ask the customers, what is your typical EKS adoption journey is looking like? These were the three major stages that they shared with us. That is finding and provisioning the right EC2 instance to power the data plane. Install, as in find first, and then install and maintain the plugins that's required to sort of operate production scale cluster. And then your day-to operations of maintaining the data plane nodes, updating the cluster, making sure it's always secure and up to date. We were told that this requires significant time commitment and investment from our customers. So we thought, how can we offload this heavy lifting from our customers and make it easy for them? So we launched Amazon EKS Auto Mode. What it does is it effectively automates cluster deployment and gives you a production-ready Kubernetes cluster with sensible capabilities built in. We're talking pod networking, we're talking load balancing, we're talking storage support. It will also dynamically provision the right compute for your application. It will scale up or down depending on what your application needs. It will also simplify your data operations in terms of it will push automatic updates to the nodes. It will make sure that your data plane node is always in sync with the Kubernetes version that's running on your control plane. So yeah, what it does for our customers is, one, it increases agility because you drastically reduce the time it takes to deploy the cluster so that you're able to quickly deploy new features and application and go to market quickly. It also improves your security, performance, and reliability posture simply because it dynamically scales up or down your data plane. It makes sure that the nodes are always secure and up to date. Additionally, it will also give you cost-saving benefits because data plane is always being continuously assessed by EKS Auto Mode. And if it finds an opportunity where it can consolidate and move it to a different EC2 instance family or a different size, it's going to go ahead and do that. So in order to appreciate what EKS Auto Mode does, we have to understand how EKS was being used by customers previously, right? So first, you decide that you want a cluster, and then you decide where to put this cluster, US East 1, Canada, whatever. And then you pick an infra as a code tool, CloudFormation, Terraform. You pick the plugins that's required to build and run a Kubernetes application. And then you pick the right EC2 instance that would work the best for your application. And then you go ahead and deploy the application. Now you continuously monitor your application and manually try to right-size your data plane so that you have cost-saving benefits without compromising on your performance and availability. Whereas with EKS Auto Mode, we have an experience within the management console. I'm not sure if anyone has tried it. It would almost give you a one-click deployed production-ready cluster with pod networking, with support to storage classes, with Carpenter. Carpenter is what runs behind the scene to dynamically provision the compute instances. Once the cluster is ready, the cluster will react to the incoming pod request, and it will dynamically start provisioning your data plane instances. And throughout this process, you as an end user, you're not doing anything. All you're doing is applying your config files, and you're good to go. Additionally, the data plane will also dynamically scale up and down, and the added advantage of continuously assessing the data plane to optimize cost.
The people online is complaining they don't see the full presentation, but it looks great here.
Okay, all right. So this is what an EKS cluster architecture looks like before EKS Auto Mode or without EKS Auto Mode. And as you can see on the left, we manage the control plane, all the components within the control plane, and the core primitives that's required to run the control plane, we are going to manage it. On the other side, you see the customers manage the add-ons required to run the cluster, the EC2 instance in itself, and other supporting AWS services like load balancers, EBS volumes for block storage, et cetera, et cetera. Whereas this is what the architecture looks like with Auto Mode. And right off the bat, you would notice that we're taking more responsibility in terms of undifferentiated heavy lifting of the infrastructure. On top of managing the control plane, with Auto Mode, we'll manage the core capabilities of the cluster. On top of that, we will also manage the data plane compute instances through what we call EC2 managed instances. And the AMI that's being used by these instances is also managed by AWS. Whereas all the supporting services that's required to run your application efficiently and any kind of other capabilities that you need on top of what is already provided by the cluster, you're going to control and manage it. And if you look at the shared responsibility model, and for folks who are not aware of shared responsibility model is with which AWS enables security for our customers. To put it shortly, whatever is on gray is managed by AWS, whatever is colorful is managed by a customer. So we manage our global infrastructure, foundational services, and the control plane in itself. Everything above that is managed by our customers, which includes compute, auto-scaling, load balancing, your lifecycle management of your data plane, your data operations, the actual application, VPC configuration, et cetera, et cetera. Whereas this is what the shared responsibility looks like with Auto Mode. And right off the bat, you would notice that we're taking more responsibility. On top of the EKS control plane, we're also managing the cluster capabilities, as in we're going to provision the cluster, we're going to manage the lifecycle of the cluster data plane, and we're also going to manage the monitoring, patching of the operating system within the cluster. We are also going to manage the core capabilities that's provided to the cluster through EKS Auto Mode. The customers are still going to be responsible for the VPC infrastructure, application configurations, and everything about that. So I want to dive a little deeper into some of these core cluster capabilities and all these four verticals: compute, networking, storage, and security. In terms of compute, we already established that Carpenter runs behind the scene. So how we achieve dynamic provisioning is through Carpenter. So EKS Auto Mode will react to the incoming pod request, and it will dynamically pick the right EC2 instance, provision it for you, and it will start managing those instances. Now, how do we achieve that? We enable that through node pools. Node pools is essentially like your regular YAML config file, where you pass down your EC2 attributes, telling EKS Auto Mode what kind of EC2 instance that you can go ahead and pick and provision for me. You can also place other restrictions on the node pool, like disruption budget, for example. By default, when you deploy an EKS Auto Mode, you would get two types of node pools. One is general purpose, the other one is system node pool. And it is recommended that you don't edit the default node pools, you can go ahead and issue a kubectl edit command and edit the default node pool, but the service will reconcile it. So it's not recommended. And yeah, this is how the configuration of a general purpose node pool is going to look like. And there are a couple of things I want to highlight here real quick. So right at the top, if you notice the budget, by default, disruption is set to 10%. So at any point in time, auto mode will not disrupt more than 10% of the nodes when it's trying to consolidate. And it's going to wait 30 seconds before it begins the consolidation process. And right under requirements, this is where you tell EKS Auto Mode what kind of EC2 configurations that you want the cluster to go and pick for your data plane. In this specific general purpose node pool, this is set up in a way that it could support wide variety of tasks. So you see that it will go and pick C or M or R category of instances. But you can create your own custom node pool if this general purpose node pool doesn't fit your requirement, and this can be disabled as well. This is the configuration of the default system node pool, and it is on system node pools. We are going to manage the core cluster capabilities that has been provided as part of EKS Auto Mode. And one other thing I want to highlight here is right at the bottom. The system node pool is already tainted with a no schedule effect with a key critical add-on. So the recommendation is not to schedule any of your application pods on system node pool. And if you want to bring in other core cluster capabilities, any other additional plugins on those pods, place the required tolerations so that EKS Auto Mode will go ahead and provision the additional plugins into the system node pool. And this is an example of how you can, define your own node pool. Let's say it's a special use case. It's an AI/ML workload. In this example, again, it's an AI/ML example, and it's going to go and pick Inferentia family of chips, which is one of our chips optimized to run AI/ML workloads. So by this way, you can create your own custom node pool and tell EKS Auto Mode cluster to not use the default general purpose node pool that was provided and use the custom node pool by placing weights or by placing taints or any kind of constraints on the pod configuration. EKS Auto Mode will also respect the scheduling constraints that I have put in place. And here's an example. So we tell the cluster to go ahead and create on-demand or spot instances. But on the pod, I'm placing a node affinity to place the pod in a spot instance. So EKS Auto Mode is going to respect this restriction put in place. And this is an example of how EKS Auto Mode consolidates if there is underutilized compute infrastructure. For example, here there are 4 instances running and 2 instances are obviously underutilized. So as per the default configuration, it's going to wait 30 seconds before it begins the consolidation process. And then it's going to reschedule those pods and kill the underutilized nodes. In terms of networking, things like CoreDNS, VPC CNI, kubeproxy, all those come pre-installed on all nodes that is being provisioned by EKS Auto Mode cluster. And it is run as systemd services. We run these directly on the host operating system. So it does 2 things. It removes the responsibility out of Kubernetes. Second, it pushes the responsibility to AWS to manage these core cluster capabilities. And load balancer controller will also come pre-installed in all the nodes that's being deployed by the cluster. And it will satisfy ingress resource and service resource by deploying application load balancer or network load balancer. You do have to create a new ingress class at the time of launch. And this capability will also managed by the cluster, and it is run as systemd service on the host operating system. In terms of storage, EBS CSI driver, EBS CSI node agent will also come pre-installed and will be run as systemd on the host operating system. We do have a new provisioner. If you're using storage class, you just have to create a new storage class at the time of launch, referring to the new provisioner. And this is an example of doing that. Yeah, in terms of security, EKS pod agent identity. So this is what will be used by your Kubernetes application to obtain IAM permissions to talk with downstream AWS services. This will also come pre-installed on all the nodes that's being provisioned by EKS Auto Mode, and it is also run as systemd service. And yeah, the command here shows with AWS CLI how to create a pod identity association, and that is essential for pod identity agent to work. And so I kept saying that all these core cluster capabilities are run as systemd services on the operating system. The operating system that we use, again, a managed AMI, is BottleRocket. This is an extremely lean, minimal operating system optimized to run containers built by AWS, and it's open source. It doesn't have any of your package managers that's present in traditional Linux distributions, and the file system is read-only. And one of the reasons why BottleRocket doesn't have a package manager is we don't go ahead and update every single component within the system. It's almost like your smartphone update. It updates the whole unit. And it is BottleRocket that enables us to bring the responsibility closer to AWS to manage all those core cluster capabilities. And in terms of security, like every other AWS service, security is built by default into the service. And BottleRocket is one of the mechanisms through which we enable security. It doesn't have SSH access, SC Linux enforced by default. As I said, it's root-only file system, so it's immutable. So when there is a new version of any component available, we'll publish a new managed AMI. And Auto Mode will detect the availability of new AMI, and it will gracefully update your entire data plane nodes to the new AMI. And it is through this, we are also automating security and patches to the system. And if any of your data plane nodes are drifting from your control plane Kubernetes version, Auto Mode will detect it and will gracefully update those nodes to match that of the control plane Kubernetes version. And it will completely respect your disruption budgets and other pod requirements that you put in place. So this is an example of how you would trigger a EKS version upgrade. So you find a new version of Kubernetes available, you verify it, you trigger a control plane upgrade, control plane updates, followed by the managed cluster capabilities, followed by all the nodes in your data plane. And throughout this process of updating the nodes, as in it's going to, all these are ephemeral compute, it's going to sort of discard this compute and create a new compute instance in place. While it's doing that, it's going to respect your your no disruption policies. So yeah, I know it was a lot of theoretical topic, and talking through microphone is not comfortable, guys. We need another microphone. But that being said, putting all of this together, I have an application, it's Friday evening. I want to deploy it as quickly as possible. I don't have a lot of time. What do? I go to the console, create an Auto Mode EKS cluster. I create an ingress class or a storage class. I apply my config files in terms of service, deployment, ingress, and maybe I put in a metric server and pick an observability tool, and that's it. I have my application running in a production-ready cluster, externally exposed, stateful, and that will accommodate and scale up and down depending on my application's need. So I want to leave you with these 4 key takeaways before I hand it over to Matt to show a live of what exactly I just spoke about. One, because it drastically reduces the time to deploy a cluster, it increases your agility. How quickly you can innovate a new feature and go to market, this drastically improves. It also drastically reduces the operational overhead because you're not managing the data plane, you're not managing any core cluster capabilities that came with it. You're only going to manage the entire application in itself and additional plugins that you're bringing in. And because it continuously assesses the data plane for right-sizing opportunity, you're also going to get cost-saving benefits. And the service in itself for the cluster is secure by default. And we enable security through various other mechanisms I just discussed. And yeah, I'm going to call upon Matt to show a live preview of this or demo of this feature. And thank you so much, guys. It's after the game.
Share the desktop. Right, the toolbar is in the middle of the screen. Okay, sure. Oh, look. All right, so how much time does it take for you to spin up a new Kubernetes cluster? Anybody can do it in under an hour? The font thing is. Who can do it under an hour? What were you using? GCP? Under an hour. All right. So in AWS, it takes about 10 minutes to get an EKS cluster, which is exactly what I did. Funnily enough, I did enable auto mode on it. There's no nodes. There's no pods, and there's actually no nodes if you look at it. Not very useful, but there's a lot of hidden stuff in auto mode. We did talk about managed carpenter, for example. So let me jump into the console here. So my cluster is called Extravagant Disco Crow. And if you're not too familiar with the add-ons of AWS, there's a lot of stuff we do publish. But let's say you want to install the metric server because you'll be doing some auto scaling with HPA and stuff like that, right? So you select what you want to install, and then you find the submit button, right? You can select, some of them have multiple versions. The metric server doesn't have too much. And then you do the create command. At that point, you can put a watch on your cluster. You just open this one. Oh, you want to louder. All right, so the pods are being created at that point. There was no node, remember, right? So what will happen, you think? Nodes, how? Carpenter. So there is a managed carpenter. So if we look, and there was not too much people familiar with Carpenter, but Carpenter used something we call node pools to decide which type of nodes to provision. That was a constraint that Vignesh did show up. So by you can enable two built-in node pools. One of them is called system, and the other one is called general purpose. So the commands where there's two now, the lines where there's two is kind of giving up. So since the metric server is a critical add-ons, right, it will go to the system node pool, right? So at this moment, Carpenter is usually pretty fast. So 43 seconds here, the node to join. And if we look again, our pods are actually starting up. We're in about 70 seconds. This is quite typical in the speed of Carpenter bringing up nodes. It will vary, if you bring the bigger nodes with GPUs, those kind of thing. They're a little bit slower to start, but a minute to 2 minutes is quite realistic in time to expect for nodes to join. So we just installed metric server. So now we have a cluster, and we see we have a managed carpenter. So what next do we do? Somebody wants to install some kind of a web application, maybe? I see nodding. Yeah, all right. So let's do that. I can prepare a little bit. So I do have, if I go in the right folder, I do have a couple of Helm charts I can install. So nothing fancy here. I'll just run the script. It install 6 different Helm charts with different services that will be installed in our cluster. So it takes, still has to pull some of the Helm charts, stuff like this. Usually not that long. I'm not sure what's, there's a god called demo, right? And he always comes at that moment. Let's give him a couple seconds. Yeah, it waits for the call, but usually it does not. It was very fast last time I did it. Yeah, all right. So it took a couple, seconds for the first half. It probably bring up nodes because there was no nodes at all. So, I had to wait a little bit. So, this is boring to watch. So let's spin up another window. And at least we'll be able to see the node come in. All right, so there is this big enough. All right, so we see the pods are actually slowly starting up. Right, so, while this is happening, you can check. You now have multiple nodes, right? If we actually check, they are, they're using Bottle Rocket. So if, Vignesh did talk about this. So this is the container optimized OS built by Amazon. Works really differently from traditional Linux hosts, but, they do bring extra values to it. Very similar to CoreOS, yes. So now we have one node in each of our node pools, right? So the metric server is running on one node, and or other add-ons is running there. So what is also interesting is right now there is no PVC, no, we didn't expose, so there's no service or no ingress controller. So I can, right? There's none of them yet, right? So I did have a modified UI, right? And I'm sure you know about topology spread constraint and how to ensure your pods are on different nodes and those kind of things. So I will, I'll skip that one unless somebody says you should show that now.
Is this like the anti-affinity?
It's very similar, yes. Yes. Right. So we do recommend topology spread constraint. There is a little bit of more flexibility to it. So, depending on your use case, one or the other one is usually good. So I'll go directly into enabling an ingress controller. So you're familiar with ingress inside of Kubernetes, right? In AWS, you'll provision an application load balancer, and usually you run a component called the AWS load balancer controller to do that. And with Auto Mode, you don't actually see it, but it's actually there. So you just have to basically override this with this window. The Helm chart, right? We just, inject the value to the ingress. And the AWS load balancer controller will basically go provision the AWS resources for us. We don't have to, manage that component anymore. The EKS Auto Mode will handle all of this. Right? So now if we check the ingress, we have a load balancer coming in. Of course, if I try to, to provision load balancers in AWS, DNS propagation takes a minute or two. So it will eventually come online, but we have to wait for it to happen. Now, one of the interesting questions we sometimes get when people start playing with Auto Mode is, when Carpenter was doing something, I was actually checking the logs. So how do I do this if I don't see the Carpenter actually running in my cluster? So most of the interesting thing is actually now available in the events of Kubernetes. Sorry, type correctly. Sorry, I'm looking for. Oh, right. So if you do the get events, you will actually see the Carpenter actually spin up. This is not very readable on screen because of the big font, but it is the information is there. And for one of the reasons is this is not ordered by the API server, which always in my mind's why, but this is how it is. Creation timestamp. So now if you ask Kubernetes to sort it correctly, you kind of have something which is a little bit more meaningful with the the latest event at the bottom. So you kind of can fold this. So now, and at this point, we should It's not quite there yet. Although pods are actually running. And we still only have 2 nodes, right? One of the system and one of the general purpose. So if you've never seen Carpenter in action, it's kind of a very flexible. I can do dynamic sizing of the nodes and all of this, something that cluster autoscaler do have a little bit of issue with. So what we can do is basically spin up a very big number of nodes, you know, in the matter of a couple of minutes. So I think we should, whenever my load balancer comes in, we should actually stress my auto mode cluster and see how much nodes we can spin up. So how many? Let somebody pick a number between 100 and 1,000, and we'll spin up that amount of pods. How? Somebody want to share a number? 682. That's a very interesting number. Actually. Always whenever people. All right. So we do have the load balancer just came in. So as you can see, you know, this is the traditional e-commerce application, sample application that we use. There's you know, different services for the cart, the checkout, those kind of things, right? This is all running in my cluster right now. There's even databases running in my Kubernetes cluster. You know, we don't traditionally recommend to run databases in Kubernetes, but you know, for a demo or you know, some kind of, you know, it's perfectly fine. So at this point, right, we do have a couple of deployment. So let's scale the actual UI, right? Because that's what is taking most capacity, right? Because you know, this is Black Friday, you're selling a lot of watches, right? So at this point, we can do a zero watch on our deploy, right? So the pods are being created. And at this point, the get events. Copy this command somewhere. Right. So it's telling us, hey, your nodes are full, right? We will add new nodes. You know, if we do a watch at this point, as we can see, there's one node that just came online. What could be interesting here, if I extend the labels, is that node is a C6A large. Who's familiar with the Graviton, the ARM processor from AWS? See a couple of people. So interestingly, the default node pool for application does not include Gravitons, because a lot of people don't build their, you know, their pods for Graviton, those kind of things. But the system node pools do include Graviton built in, especially since most of the add-ons is coming from AWS. So as you can see here, whoops, it just went off screen. We're using a C6G, which is a Graviton node in your cluster. So without doing too much with Auto Mode, you will be using Graviton and gaining some of the performance cost benefit of it. Yes, those are ARM processors. So I think it's actually replacing our nodes with bigger node now, since there is capacity here. What is our... There's only 2 pods. What could be happening, actually? Let's check the event here. So there is a couple of things happening. Let's give it a second, see what's going on. I don't want to. Oh, you know what? Maybe happening. I'm getting throttle on pulling those images. Is that? There should not be anything here, but it says incompatible with no pool general purpose. Topology zone exists. Did I add a zone? Oh, it's probably because I force the topology, which should be fine. So Carpenter should bring up a node in the third AZ here, and it's not actually doing it. So not sure what's happening. So let's remove that part. Just so we're not stuck here. Right, it's probably cleaning up all my pods since my Helm chart, I brought that back to 2, to 1 actually. All right, let's do the scaling again. See how it goes. Yeah, so hopefully it's a little bit better. All right, so now Carpenter should be able to bring up nodes. Should be only a matter of a couple seconds. There we go. All right, so our nodes is coming up online. New nodes. And then if we do get deploy, you should see the number of pods going online up pretty quick when a few nodes get in. Yeah, so 7 of them are available now. 400 of them have been scheduled on specific nodes, so they're slowly, doing the health checks that we all know, built into Kubernetes, and basically bringing up online capacity for our UI to scale. Not 10 people move from 1 pod to 600 something, but it is, in a matter of a minute here, you'll get the capacity you need. This is very efficient to bring up all kind of nodes. Yeah, you can use also all the nodes from AWS are basically compatible with EKS, with a few exceptions. Like, don't ask me about the Mac nodes or something like this, but they can bring it those nodes, including Graviton, including Spot Instance. All of this is actually compatible. Is there any question on Auto Mode? Sure. Yes. So the overall strategy of upgrades is to be as seamless as possible. All right. There's something, and this is in all Kubernetes cluster called upgrade insights. So this is, I'm showing you from the console, but there's actually an API for it. So if you go into your console, the upgrade insights will tell you if something in your cluster is used, deprecated API in the last 30 days, those kind of things. From there, you probably will have some action, either some component to updates or some application to change. But the goal of Auto Mode is to basically be able to auto upgrade at that point if there's nothing that's being flagged, right? So that is there is definitely features coming up for this inside of your clusters. Inside of
I have a for example, I have MSK, say MSK will be there will be maintenance window at this time, and it just happens seamlessly. Is that the same logic? Does it get upgraded at some point in time?
Yes.
Oh.
Yes. Yeah. Right now the automatic upgrade is not there yet, so you cannot define maintenance window, but that's the ultimate goal. Yes. One interesting thing, you can start using auto mode on Kubernetes 129 and above, which is all the standard support version of EKS today. Yes. So it's always good to test, but you can enable auto mode on an existing cluster as long as it's 129 and above. So it will basically install, and you can mix and match regular nodes in a cluster with the node managed by the managed carpenter tool. That is possible. Yeah. Yeah.
But if we already have carpenter, we should be better.
So it's not exactly the same. I can right. So the managed carpenter is using you see nodeclaims.carpenter.sh, while the open source carpenter use nodeclaim.eks.amazon.aws.com. So there is it will not cause conflict, but I'm sure if we're creative, we can find a way to break something, right? So just be cautious a little bit, but it is possible to enable in the existing cluster. And by default, it will not do much on your existing node. So it's, there's not too much risk.
Right. So your demo, you are scaling up a lot of nodes, right?
Yes.
Fine, but real life. So is there any ways to break the walls? You don't have a lot of machines, just in case you don't have surprising.
Sorry, you said so not have surprises in terms of nodes?
Yeah, because you are scaling out a lot of people, right?
Yeah.
Maybe scenario that I cannot have best more than 4 nodes or something like that, right? Is there any way to create a limitation or when you want to not scale more?
Yes. So in the default node pools, there is no limits. But you can disable the default node pools if you want. And basically create your own node pools. And there is a limit that you can put in terms of number of memory or CPU, the maximum that carpenter should provision. Yes. But if you think about what Kubernetes really allows you to do, it really decouples your application layer from your infrastructure layer. So I think that's the wrong question, because you should have limits in number of replicas of your application, and your infrastructure layer should be as easy as it is to manage. Don't worry too much about how much nodes that actually represent. Of course, people will say, the billing comes with the real infrastructure, but yes. Any other question?
The nodes want to scale to 0 if I have my port switch 0.
Very good question. Since I'm being billed for this cluster, I will shut down my pods here. Right, so we have, we're 600 here. So let's do the reverse. Oops. So to be fair here, to delete everything, I need to delete all my Helm charts. But basically, yes. I don't know if you remember in one of the slides that Vinesh did show up, there was a constellation after, and there was a 30-second. So basically, Carpenter will wait 30 seconds for nodes to be empty before removing them. That's a setting you can override in your own node pools. And that's something we see a lot, especially with people like you using Worker for like their CI/CD pipeline, right? Developers tend to build, and then spend a couple of minutes fixing a bug, and then they launch another build, right? Like so putting like 5 minutes to keep the node so it doesn't like go away and come back is actually something interesting. So I'm sorry for the typing. The microphone is picking up my finger. Right, so we don't have any deploy anymore, right? So our pods are pretty slim right now. So our nodes will slowly go away. So if we put a watch on this, within 30 seconds, and Carpenter has a default setting of 10% disruption at a time. So we have what, about 10 nodes here. So it will remove one node at a time. Sorry, and wait about 30 seconds before doing the next node. So, but it will slowly shrink the cluster in this case. Any other question? All right.
So in the presentation, so shown that the DNS and proxy and yeah, so it's gonna say system D process node as a container. So is that something to do with this auto scaling?
So core DNS is running on all the nodes of Auto Mode. Is that kind of your question? Yeah. So you don't have to run core DNS. If you only have Auto Mode nodes in your cluster, you don't have to run core DNS. Right? If you do kind of a hybrid approach with managed node groups, you know your managed node groups still need core DNS to function correctly. All right. So yeah, we do see here there's a lot of nodes being reclaimed. Carpenter use a finalizer to ensure they're being shut down in EC2 and basically stop paying for all the infrastructure you purchase. All right. I'll pass the ball back to the admin.
Thank you, AWS team, for the presentation. Sure. So now I'll invite Yashwardhan to continue with his session, and he would be presenting on Kubernetes controllers and operators. And just a gist, we have a small giveaway quiz as well in the end, so hang tight here. And we have some pepperoni pizza outside, so if you want to grab a snack, though. What are you doing? Yeah, you sure.
I minimize this with this.
Sure.
Yeah, so do you mind if I steal a screen for a second?
Yeah.
So I'm really sorry about this. If you guys, we're actually looking for feedback on Auto Mode and you know, all the present.
Is on. Thank you. All right, I think I should just use this. Okay, awesome. All right. Wait, why is this? It's not okay. I need to mirror this. Let me just confirm that. The mic open. Okay, perfect.
Fine.
Anyway, this interface is looking a bit different, but yeah. Okay, hi. So first of all, shout out to Matt and Vignesh. That was a pretty cool presentation. Loved it. All right. So I'll just like leave the full screen mode and straight away start. So, okay. So hi guys, I'm Yash, and currently a software engineer in the platforms team of this company called OP Labs. It works on developing the optimism protocol for scaling up Ethereum on a day-to-day basis. And I recently graduated from University of Waterloo. I love a bunch of stuff around cloud native tech and backend engineering and distributed systems. And in my free time, I also love to do long distance runs. So, okay, moving on. So what is Kubernetes? Pretty advanced question. Yeah, it's a container orchestrator. It helps you manage, schedule, automate containerized workloads, and just saves the system administrators from pulling their hair when using containers in production, especially with tools like EKS Auto Mode. So that's pretty cool. Okay, so let's talk about the nature of Kubernetes, right? It's level triggered and state driven. What does that mean? It basically takes this concept from the good old digital electronics, where how your CPU talks with hardware, various hardware. So your hardware can kind of request CPU through either like pulses, which is like edge triggering, or just setting a pulse at a certain level, which is level triggering. So the issue with edge triggering is that what if the edges and the pulses are missed? CPU won't know what to service. So Kubernetes achieves a very eventually consistent model through level triggering. And the level triggering is all about observing a certain desired state. And Kubernetes constantly very like maturely trying to reconcile the desired state with the real state. All right. So, and the real backbone of this level triggered state driven model are the controllers, right? So they're long running entities. Their only goal is to match reality with the desired state as efficiently as possible. So we're aware of so many such controllers like deployment controller, stateful set controller, daemon set controller. One example, desired state is 3 pods. You have currently 2 pods. Deployment observes that and reconciles that. So it's an observe, analyze, act loop kind of thing. So let's take a quick detour towards operators. Again, they're just like application specific controllers. So Kubernetes has a really cool plugin like model where you can literally extend Kubernetes by programming your own controllers. So hypothetically, you can create your own thing. You can signal that controller and it's going to open a garage door in your place. Actually, one of my friends did that. So that's pretty crazy. It essentially resembles a human operator in the sense that it keeps performing tasks to match reality with desired state, like a potential administrator of a Kubernetes cluster would do. So it's a pretty cool thing. And the custom resources are the front end of operators. You tell the desired state through the means of a custom resource to this operator, and this operator exactly knows how to parse it and match the reality with the desired state. Right. And then like just like any other resource, you can do kubectl get, apply, patch, whatever you want with that custom resource. One super quick example is that hypothetical, let's say we have a operator which watches for this custom resource, parses it, and on the basis of the details in it, it writes a row to the PostgreSDB. I know it sounds a bit futile, but for the sake of an example, it's pretty visual enough. And behind the scenes, again, it's a long-running operator, it's a long-running entity which is constantly watching for this resource. And upon watching it, performs inserts in the DB. So this is a pretty custom use case. Just like that, there are very fancy operators out there handling the situation. Now, if you really think about it, Kubernetes is just a backend API in a way, right? And it just like a simple backend API, it has a database. The database is etcd. And any resource which you are, any kind of interaction which you are having with Kubernetes is a bunch of CRUD operations behind the scenes. For example, when you kubectl apply or create a resource, behind the scenes, essentially a post request is happening of some sorts, right? And this is a very cool picture I got from this guy called Eximus. I've referred to him as well. Lovely content he posts. So you can check it out. But a fundamental, like you can see that every resource somehow is leading to a REST-like looking endpoint. So you can literally curl your way through instead of kubectl. So yeah. And if you, again, like if you think on those lines, a controller is like a long running client of that Kubernetes API, right? I mean, ultimately a controller is like watching and reading the custom resources, which are just objects in the database of Kubernetes through the means of GET requests. And it reacts to them by getting a 200 response, parsing that response and doing some operation. In our case, that was like writing to a database, right? So, but does anybody spot the problems here with just the whole act of constantly getting the stuff from API server and seeing, oh, which are the new resources and should I reconcile it? Any potential problems does anyone of you spot? Let's see.
Too much try.
Yeah. And so multiple problems actually. Efficiency is one of the big problems. Tracking field level resource changes, because what happens is that anytime when the a long-running client is getting the new resource, it's only getting the perspective of the latest state. And also, although like Kubernetes like really promotes this idea of idempotency and just observing the latest state and taking decisions, there are certain optimizations you can perform if you notice the exact drift between the old state and the new state. So how do you store the previous state? And you don't want to store the entire previous state of your entire cluster, right? You have to be very specific, for example. Also, what about the periodicity? Like if your controller is too fast, constantly polling your API server, it's gonna hog it up. If it's too slow, it's bad user experience, slow consistency. Also, how about tracking results? Like how are the results tracked and how is the state tracked in terms of how successful or how partially failing the reconciliation is, right? So there's a lot of things to kind of develop here. And a controller should ideally like watch the API server as efficiently as possible. And yes, it should be level triggered, but it should leverage the edge triggering wherever possible. It should still try to watch for newly incoming events as much as possible. That provides like quite pseudo strong consistency. Also maintain a certain structure of custom resources to have a section to states and whatnot. Ideally, it should have a storage backend, an efficient one like a cache, which helps it track the old states of the resources it's watching so that it can take certain optimized decisions on the basis of the drift between the new state and the old state. Also, to avoid thundering herd problems and when busy situations happen, it should have like concurrency, safe rate limiting queues and whatnot for those kind of situations. So, I mean, writing that stuff is a nightmare. So the Kubernetes folks developed a library called ClientGo. And what ClientGo is, it's again, it's a client written in Go, fairly obvious from the name, but it's like an SDK client to supercharge dealing with Kubernetes APIs. Yeah, and it helps maintain resources like things like caches, queues, and whatnot out of the box for highly efficient Kubernetes controller and operator programming. Also, it helps you develop and inject webhook-like event handlers to your controllers so that whenever new stuff happens in your cluster, like let's say your controller is watching over newly incoming pods for some custom logic, you can attach like, okay, when a pod is added, what happens? When it's updated, what happens? So these kind of very efficient way of injecting functions, it provides support for that. Also, it abstracts away a very efficient watch connection with the API server because short polling is very heavy on the API server. It's intense, it's inefficient, right? And there is a way through server-side events that this library provides you support to establish like a pipe of some sorts, a long-running connection, where whenever a new resource is created in the API server, it is straight away informed to the to your controller that, hey, here's a new resource. So this is pretty efficient. A bunch of like network IO optimizations happen here and whatnot. And finally, your controllers are also backed by a bunch of queues for busy situations, for thundering herd and whatnot out of the box. So it's a pretty cool library. And it might sound intense in the beginning, but its interface is quite convenient to deal with. We're going to explore that later. So the idea is fairly simple, like just to give a vibe of how you talk to your Kubernetes cluster through ClientGo. So one way of talking to Kubernetes cluster is kubectl, right? We use terminal, execute a bunch of commands, and magically we get the pods and nodes. But behind the scenes, how is your terminal authenticated, or how does it even know that where is your Kubernetes cluster out there in the world? So your kube config holds that information. Behind the scenes, it's an environment variable which tells your terminal. In our code, we injected through this line of code that, hey, here is a certain place where I have the kube config. And I feed that to ClientGo, and it gives me an object called client set. I've named it client set. But this object is the entry point for talking to your Kubernetes cluster. And so this is how talking to Kubernetes cluster looks like. I mean, I have in a very nice typed, like statically typed manner, I've defined what a pod I want to spin up, which is an Nginx pod running Nginx 1-to-1. And like it's as simple as just calling this one line to create that pod. Similarly, you can get that pod again through the means of options. You can list those pods in a certain namespace and whatnot. So in a very type-safe programmatic manner, it's helping you deal with the Kubernetes cluster. But I'm just barely scratching the surface here. Also, polling is slow, as shown in the diagram. So you can also establish a watch connection, literally a watch connection with your API server, and tell it that exactly what do you want. So in our case, I want to watch all the pods coming in my namespace, and I get a channel, a Go channel of some sorts as a returned output. And then I can just run a loop against this channel. And anytime, literally, when API server observes a newly incoming pod, it literally sends this stream of output that, hey, an event like added happened for a pod foo, in our case, Nginx. And then one of the switch cases can handle that situation. If it's an added kind of event, you can have a certain function, let's say emailing you that, hey, suddenly a pod appeared out of thin air. And if you want to parse the details of the pod, the event itself contains the details of your pod. You just like marshal it into the pod and boom, you're done. So that's pretty convenient in my opinion. But this also has a bunch of gaps, to be honest. Like there is still, I didn't show you the cache kind of situation and whatnot. And this is where informers come into the picture. Informers are the backbone of writing efficient Kubernetes operators. All those gaps I talked about, like caches, queues, and whatnot, that is something which is dealt with the help of informers. Now, as I mentioned, that watch is an efficient way to watch for resources, and that's what it does out of the box. It watches your resources. It helps you register event handlers to various events. Now, one more thing I missed in the previous, when I like set up this watch connection, in the modified event, you don't have any access to what was the previous state of the object. You are still having the access to only the latest state of the object, because think about this kind of communication, right? API server is just telling that, hey, something is updated. That's it. It's a kubeshell patch or anything. API server is not smart enough to know that, hey, I care about knowing old state level information. So that level of also capability is baked into the informer, right? And yeah, so when you're registering event handlers, you'll notice later that the update event handler is capable of having access to the old state of the object as well. And how does it have that? Because behind the scenes, it's maintaining a very efficient cache of the old state being observed, right? Finally, it's backed by a bunch of queues, which are concurrency safe. They have a lot of deduplication built into them. And there is definitely no thundering hurt because they have a nice capacity. If there are busy situations, a bunch of stuff can sit pending nicely in those queues and eventually reconciled. So, yeah.
What are the details available on? So I see event type.
Only two. So event type and event object. So what's happening with the object and what is that object? Rest you can take care of it. You can marshal it into pod, and the pod or object itself has everything you want regarding that detail. So yeah. Awesome. So informers in action. So the idea of informers is that usually you don't create informer like one by one basis. And let me just like try to demystify this informer term even further. Let's say I'm creating a controller which wants to watch pods and config maps. Let's say hypothetically. So usually we tend to have like a one-on-one correlation with an informer and the resource type being watched. So I'll essentially create two informers. One is a pod informer, which will be responsible for reconciling and watching pods in a cluster, and the other a separate informer, which will be responsible for watching and reconciling config maps. In the whole set of slides, I'm only showing the perspective of writing one informer, but this was just a like heads up. So yeah, in my situation, I'm kind of writing a controller which watches over the pods and does something. But before creating an informer, we create an informer factory. An informer factory is more like a parent object for informers, through which you create multiple informers like pod informer, config map informer. And the use of factory is that there's a lot of things you need to do when you start your informer in a right way. And if you are, let's say, if you have 5 informers, then I mean, you have to run a for loop and do it rightfully. So informer factory takes care of it. It's an entry point for managing all of your informers. In fact, informer factory is pretty smart actually. Like if I just copy this second line again and again and again, it's going to notice that, hey, duplicate pod informers are being added and there is no benefit of duplicate pod informers. They're going to observe the same pod and do the same thing 5 times. So it won't take them. Also, it's concurrency safe and 1,000 things it has. So yeah, in a very onion ring kind of imagination, factory is a parent object, and using that, you create different informers. In our case, we are creating the pod informer. Then this is actually, I'll come to that slide later on, to be honest. Like in my laptop, I changed the position of that slide, but yeah, I'll come to that later. But yeah, about attaching event handlers to it. So notice how I'm very conveniently attaching event handler to my pod informer. That, hey, pod informer, you are the one watching pods. I want to attach some logic to you, depending on when a pod is added, when a pod is updated, when a pod is deleted. And notice the update function. It has old object and new object interface. So that's how like it's exposing through its interface that, hey, we have access to old object and new object. And see, like I won't dive into the details, but ideally, your entire set of decisions, like functional decisions, should be based out of the new object, the desired state. But definitely, sometimes there are certain optimizations which can happen if you happen to have access to the old object, like exactly which field attributes changed, right? So it's a nice to have. It's a nice to have. All right. And then that's it. Like starting the informer is as simple as just like creating a stop channel for signaling stop situations to the factory. But I just did a factory start, and whichever set of informers, 5 informers, 15 informers it was aware of, it would start behind the scenes very efficiently, right? And that's it. It would run. And this is how a live output would look like. This is a consequence of like, I just did an FMT print and like I just print logged the events happening, and you can see that event type is usually this capitalized string of added, modified, deleted, and all these pods are okay. And also what happens is that whenever an informer starts, like it does not start from zero. The first thing it does is it does a cache sync or list operation. So ultimately, as I mentioned, that it also tracks the old state of the resources which were already existent, right? So that when updates happen, it knows that, hey, an update happened. So during its startup phase, in a warm-up phase, it kind of lists all the pods existing in your cluster and kind of caches them. So it's a warm-up phase, and that's why like suddenly the moment I started them, although these pods would have like added half an hour back or something, they were like still like from the perspective of controller added because it loaded them in its list. So I think this maybe does not look deep enough. So I think we can foresee this thing, but yeah, time for some depth. But before that, let's sort out a quick concept, which is cache versus index in the pod. Oh, sorry, in the informer. So the idea of caching is that ultimately we want performance, and an operator, a controller is constantly, actually informer, is constantly watching the cluster. A bunch of CRUD of the observed resource can be potentially happening as well. So you might as well cache that resource, right? So it behind the scenes maintains a cache. And the idea is that for every object it observes, it caches that resource in its cache. And it's an in-memory hash map, to be honest, where the key is simple, namespace, name combination, obviously. And the value is the actual object being cached. So the entire pod object. And that's the beauty. Like I can just straight up ask the cache that, hey, what is the default /nginx pod? And it's going to give me all the information in O of 1 time. So that's pretty cool. But sometimes what happens is that just caching by a namespace and name combination is not good enough. Let's say you have a certain situation where you want to efficiently query all the pods in a cluster on the basis of the image they possess. Like if I have 1,000 pods, or let's say 682 pods in my cluster, and let's say I want to see that which subset of the pods in them have Nginx running in them. Maybe 300 of them have Nginx running in them. How do I do that? Like I don't want to do a massive CRUD operation. So just like any database, I create an index of my own, where index is again another hash map, where the key is the image, the custom caching key we are setting, and value is the list of references to the pods which have those image, right? And this whole translation, that from where is this image coming from, I mean, that is provided through an index function which you write. Index function essentially is like this: hey, the input is pod being observed, just go through all of its containers under the spec and parse the image, form a slice, and that's going to be the result. So for Nginx, the like value is the list of keys in the cache which correspond to the one holding Nginx, right? So that's fundamentally the idea behind cache versus index, and that's exactly the reason why I skipped that slide. Like this is a slide through which I'm actually setting up that kind of cache, that I'm just telling my pod informer that add an indexer. So in this situation, for the time being, indexer is like a index. So let's just consider that. But yeah, I'm just telling that the name of my indexer is by image. Correction, I did not want to edit the image. I was lazy. But yeah, by image. And again, the function is simple, that any object which is observed, okay, it's going to be, I'm confident that it's going to be a pod. So I'm marshalling it to a pod. And then I'm just going through all the containers, parsing the image and returning the slice of images. So essentially, I'm taking the input as the value, so the object as the input value, and outputting the slice of keys in the cache. Oh, sorry, so a slice of keys in the index which it points to. Yeah. So that's how it looks in runtime. And I think we are pretty sorted. So this is how the user interaction would look. That as a user or as a whatever developer, I literally enter that, hey, informer, I want to get the pods with the SQLite image, and input is SQLite. And I also mentioned that, hey, I want to fetch it from a certain index. That index will realize that, hey, the image is SQLite. let me go through all my stuff, and it's gonna output the keys in the cache associated with those pods. And the output is going to be like this: default nginx, whichever set of pod keys, and these keys will be routed to the cache. And this cache will simply just look at these keys, fetch the corresponding values, and return them to the user. And that's how you efficiently get, like custom caching kind of logic simulated in your situation, just like an index. So TLDR, one informer factory consists of 1 over informers. Every informer consists of one cache. And an informer can have 0 or more indexes depending on how many custom caching logics you want. The whole namespace name combination kind of caching is the default one. And an indexer is just an index with a name for now. So pretty much an index. There is another usage of indexer which is going to come later, but it's not my fault. Client Go folks really jargonize things in a conflicted manner. But yeah. So yeah, the anatomy, we want to understand that. Yes.
Like you do different inflection.
Hmm?
That looks like so after adding an index, so you want to use the go get line.
This line. Okay. So I'm telling pods informer get indexer by index, the name of the cache or index I created, sorry, not cache, index, and the input SQLite. That's it. So usually that's pretty rare. I mean, like I would imagine only in custom solution like CNI interfaces and whatnot, they will be potentially caching pods by their IPs and whatnot. That's pretty normal, but I've rarely seen this kind of pattern. Usually it's through namespace name combination. So yeah. All right. So the anatomy, okay. So let's start with that onion kind of structure. So as I mentioned, informer factory is the parent of all the other informers. And it helps you start, stop, cache sync all the informers at once, deduplicate. It also deduplicates the creation of the informers. And it's very easy, like it helps you register event handlers and whatnot through the means of it. Beneath every informer is an indexer. Now this indexer is just a wrapper object which holds your underlying cache storage. It also provides helpful methods like reverse lookups from values to keys in your cache. So if I have a pod and I want to see the corresponding key in the cache, like for some special use case, it provides some functionalities like that. But the main functionality is that it helps you add those indexes, custom indexes through the means of it. And yeah. Finally, under it, it has the cache storage, like object. Again, it's a fairly abstract logical object which holds a thread safe store of your cached objects. It also holds the logic of converting an incoming pod to the cache's key. Now, remember I mentioned that the default caching logic is the namespace name-based. Well, it's not hard-coded, it's tweakable, and you can tweak at this level. So that function which parses the namespace and name combination, that sits inside the cache storage. And also the indexes end up pointing to this cache storage when they're referencing to the objects. Finally, the belle of the ball. The thread safe store is what like holds the cache and the index and even those indexing functions like which parse your incoming pods and convert them to the indexing keys. This is what holds it. And it's nothing, it's just a glorified in-memory hash map. Like it's literally an in-memory hash map. And it holds multiple indexes, as I mentioned, and just helps you quickly query these objects. So that's the purpose of it. Then I have a bunch of slides previously. They were like diving into the source code of the above things. I think I'll probably not speak about them, but I'm going to be sharing the slides with you. So you can definitely check them out and potentially that's going to be helpful. But yeah, my question is slept yet. I don't think somebody has slept yet. Some people have left yet, but yeah, anyway. But yeah, okay, nope. So let me help further. Okay, let's talk about the mechanics of a running informer. All right. So I am happy, like I don't have friends, so I run the informers and I start the informer. Again, I showed you in the previous code that it's just a run function you call on the informer factory, and whichever informers you created out of it, it's going to start them concurrently and in a pretty nice fashion. It starts them individually. Now, from the perspective of every individual informer, this is what happens. Firstly, it creates an object called controller. Now, for the sake of this talk, I'll synonymize the word controller with reflector, but there is very teeny tiny difference, but mostly they are synonymous, roughly speaking, on a source code level I'm talking about. So when you're creating the controller, majorly a bunch of entities are created, but the three main entities created are these ones: a lister watcher, a queue, a delta FIFO queue, and a processor. Okay. So the lister watcher, this entity is what is, yeah.
So question, was that being created by Kubernetes, or is that just like internal for the SDK you're using? So it's like
To the SDK, like these are just a bunch of structs, objects to the SDK. So Kubernetes, no Kubernetes API level object is being created here. Okay. Yeah. So yeah, lister watcher. Remember I mentioned that there's an entity which watches the API server. Something has to watch the API server so that like it establishes that watch connection gets the details from Kubernetes server about what's getting updated how. This is the entity which does that. Then why it has the name lister in it? Because it also performs that initial list against API server to get all the existing objects which it is supposed to watch, right? And it is smart enough to know that it's only watching pods in our case. It's not blindly watching all the resources in the cluster. And what it does is that after watching them, it enqueues them to a queue. So it's not just straight up feeding to our event handlers. It enqueues them to a queue. And that's the delta FIFO queue. Delta, this is an important word. So throughout this presentation, I've been talking about this combination of object plus what's happening with the object. So that is the event type. So in client Go, internally, there is a struct, there is a simple object called delta that just contains two attributes. What's the event type which is happening with the object and the object itself. So yeah, so basically what's happening is that the lister watcher is what takes in the incoming events that, hey, added is happening and a pod is being added. It wraps them into the delta and feeds them to the delta FIFO queue. So it's a queue of deltas, that's it. Also, there are some fun optimizations in this queue. There is a transform func which you can write on your own to optimize this queue further. So let's say you're dealing with pods, and pods have sometimes a lot of useless fields, like maybe volume mounts and whatnot, which you don't care about. And you want to hyper optimize that and be like, okay, whenever a pod comes up in this queue, I don't want to store that field. All I care about is a bunch of images, pod IPs and whatnot. So the transform func is capable of looking at this incoming pod from the lister watcher and filtering out all the fields which we don't care about. So ultimately what ends up reaching that FIFO queue is that filtered object which went through the transform function. Also, whenever this queue starts, it also is fed with the existing objects, existing cached objects, because again, whatever ends up in this queue is what gets processed later on. And we want to process all the existing objects in our cluster as well. Finally, this queue actually, just a second. So this queue simply holds the element. Now from something, all these elements reach out to a component called processor. Processor is nothing, and by the way, I'll talk about that some component a slide later, but yeah. Processor is what holds all our event handlers, all the functions you declared like on add, on update, on delete. And essentially those functions are exposed in the form of objects called listeners, but they're kind of fairly synonymous from this perspective. So yeah, ultimately all the deltas reach a processor, and the processor like, hey, this looks like an added event. Let's feed it to the on add function. This looks like an update event. Let's feed it to the update function. And that's it. Like, and also processor receives a bunch of deltas at once. So it does not have to deal with things in a one-by-one basis. Like things can be quicker when you deal with them in a batch fashion. Also, each listener internally has some sort of rate limiting through a ring buffer, through a ring-based queue. So if like your listeners and event handlers are extremely exhausted, then these kind of pending things will be queued up, and it has a size of 1024, maybe like 1 megabyte or something. Sorry, 1 mega size. So yeah, anyway, 1000. So no, 1 kilo. What am I saying? Okay. Yeah, so 1024 sized ring buffer, which is capable of, again, like very nicely rate limiting such kind of busy situations. So the final showdown is how it works in real time. This is how it looks. I do a nice kubectl create pod foo on a Sunday night because I don't have any friends. So yeah, this request reaches the API server in the form of a potential post request, and API server creates it. By now, already I have a controller operator informer running. And what it's doing is that basically it already has a watch connection established with the API server. So API server knows that anytime a pod is added or something is added, tell it to the lister watcher. Lister watcher is the one establishes the watch connection. And this event happens, added pod foo. Lister watcher realizes this event, transforms it into a delta. Again, the combination of the event type and the object. and feeds that to the queue. Now, as a part of the controller in a separate Go routine, separate thread of some sorts, there is a process loop running, and it's a very simple process loop. It's literally an infinite while loop running on a 1 second interval, like hard coded 1 second interval. And every second it looks at the queue and tries to fetch as many elements queued here as possible and just sends that slice to the processor. That's it. All it's doing that because queue does not know about processor. Queue is essentially a database, a slice-like database of these changing events. Process loop is what kind of pokes this queue, gets that data and sends that to the processor. Processor realizes that, hey, a bunch of deltas are here. Few of them are added, few of them are updated, and it sends all those relevant deltas to the relevant on-add or on-update function which we have written. And in our case, a kubectl create is happening, which is a potentially added operation. So it ends up getting routed to the on-add function with the pod object. So yeah, I mean, quite a fire hose of information, I know, but also.
So Listed Watcher only listens to the event that you registered for, or it listens to everything, but it only filters out that and pass it on to the rest of the things?
Good question. It's kind of a both. So it only watches for a certain resource type, but upon looking at the source code, it is cognizant of the fact that sometimes mistakenly it might receive another object. So it still does a comparison between what is the expected resource type and whatnot, and it registers a silent error and still continues with its job. But 99% of the times, it's going to observe a certain resource type. Awesome. So we are almost near the end, but yeah, like what else you can check out? So ClientGo is not the end all be all of writing operators. There are nice libraries called, there's a nice library called actually an SDK, but yeah, controller-runtime written, which is a wrapper over ClientGo, which provides more power and more ease with writing operators. Did not have enough time to talk about it right now. Also, KubeBuilder SDK is like a boilerplate code generator for writing operators, so very helpful. I also once upon a time wrote a blog about writing operators with KubeBuilder. Feel free to check it out. I hope you folks are going to like it. I know it's like linked there. There's no QR code per se, but I'm going to be sharing these slides later. So yeah, you can refer to them. References. So ClientGo, the main source, the code never lies. So yeah, the source code was nice. But apart from that, there was a blog around edge and level triggering logic in Kubernetes. Also, there is a very fantastic KubeCon talk about life of a Kubernetes watch event. I mean, it's really cool. Like the way the depths it explores is amazing. And just a nice blog in general about Kubernetes informers, which you can check out later. I've also attached my handles. Feel free to catch up with me, reach out to me, anything works. And again, like, thank you so much for your time, folks. I know this was a fire hose of information, but yeah, thank you. Yeah, so any questions? Sorry?
Can you go back a slide?
Yeah, for sure. Actually, let me just minimize it. What's happening? Okay. Yeah. Go back a slide. Okay. Okay.
So when you get the events, is there like an event timestamp or a sequence number so I know that I've processed this much and then if let's say I crash in the tour, I can continue from that point?
Sorry, can you repeat that about the event timestamp?
Is there an event timestamp or a sequence number? So I know that let's say my controller has crashed and recovered, I can continue from where I left off instead of starting from the top of the queue.
So I think if I understand the question about the timestamp tracking. So for updates, usually you track a number called generation in your resource in Kubernetes. So that usually gives enough information that there is a pre-increment of generation or not. That's point number one. Point number two, if a newly created pod has entered, the event inherently does not store the timestamp level information, but the creation timestamp of the resource is quite indicative of that. So yeah, rest, the operator is usually quite dumb in that sense that it just initially performs a list. Even the first time, like if there is an existing resource, right, it might think that they have been added. And that's exactly why I was mentioning that it's better to write operators in a way where you really don't care about was something added, updated, or deleted. Like you care about what is the desired state. Okay, the latest state of the pod or incoming resource is X. I need to do something. So don't always like trust if Kubernetes is saying something is added. Maybe it's a update operation, but it did not have the old state, so it perceived it as added operation. So yeah, but in this situation in ClientGo, event only stores two information, type and object. That's it. Yes.
One thing I've noticed with operators is often you can't run more than one of them, or if the use leader election or something.
Yes.
I guess, is that, like, why do you think it is that that's like such a problem?
Oh yeah. So basically the situation is you can, yeah. So there would be two reasons to run multiple operators. One for kind of potentially load balancing purposes, the other for HA. So HA is supported in leader election kind of fashion, that it's like you create 3 instances of your operator, and 2 of them are like kind of running in a standby mode. One of them is active, running as a leader. And if it goes down, it loses the leader election timeout, and boom, the other one comes up. So the HA situation is sorted out. Regarding the other thing, operators are highly stateful entities. They have like literally storage baked in into them, and they are just like blindly listening the cluster for like, hey, I want to watch this resource and deal with it. So what happens if you have multiple forcefully running instances of operators for the sake of load balancing? You wouldn't actually load balance. The reason is that each of them individually is watching a newly incoming pod, for example. So when a new pod comes up, it's not like that request is going to be routed between 3 of them. All 3 of them are going to start reconciling. And that's actually bad, because that can create a bunch of race conditions, because they might have fighting reconciliations. And usually a bunch of concurrency problems are dealt with inside Kubernetes. They have this thing called optimistic concurrency control, which provides a nice set of functionalities out of the box. But yeah, like it's just a bunch of wasted CPU cycles. So yeah. Though there is a different kind of thing you develop called admission controllers or webhooks. Those are very much deployed like a typical API server, like a typical server actually. So you can have multiple instances of them, and they will just run like a load balance fashion. But that is a totally separate topic, not related to operators. All righty. Do we have any other questions? 3, 2, 1. The silence of understanding or sleep. Okay. Okay, thank you so much, folks. Appreciate it. And again, shout out to Poojan and Ashish. Again, cool stuff, guys. Cool stuff. You can take care. Should I take a look at the chat for questions? Any? Oh, that's great. Okay, perfect. Sweet. And
All right, thank you so much. A bit overwhelming for me personally, but imposter syndrome in myself is kicking out. But let me lighten the mood. I wouldn't take more than 5 minutes. I'll quickly share the QR code, and we are going to do a quiz. And based on the top 3 winners, we have some small giveaways. But just a small disclaimer, there are some people complaining in previous meetups that they are not able to see the first question. So if you are also not able to see, it's not me, it's the platform. So blame it. And another thing, if you have already won the giveaway in previous meetups, please give some other people chance, and let's give everyone a fair chance. Allow me a moment, please, and hang here. There we go. QR code. Okay. Yeah, QR code is on the screen. Please scan and enter your name. Again, another disclaimer, if you don't see the first question up, it's not me. And yeah, the rules are same. Fastest, if the fastest you select the answer, the earlier you would be in the leaderboard. And we have 10 questions, and I wouldn't take much of it. Faster than correct answers. Yes, sure. And yeah, please, the presenters should not play the game because they already know the answers. So I'll wait for 1 or 2 minutes for everyone to join, and let's see. All right, you might want to refresh the screen and you might be on the quiz page. Yeah, I already see some people already joining, so that's a good sign. All right, let's start. First up. Which tool is specifically used for EKS administration? Argo CD, Helm, EKS CTL, or kubectl? Here we go, about 50% of them were right. EKS Auto Mode helps in hiring DevOps engineers, conducting daily stand-up calls, automatic cluster upgrades, and secrets management. Oh, I thought it was A, but never mind. Which feature does EKS Auto Mode provide that EKS Regular does not provide? Configuring S3 lifecycle policies, writing CloudFormation templates, control plane management, or fixing the YML files? Which crucial step is involved when migrating an existing EKS cluster to EKS Auto? Redeploy applications with Helm, enable EKS Auto Mode by just toggling the switch, rewrite Kubernetes manifests, or upgrade to managed node groups. That is not. I don't think toggle button is available. The fifth one. When setting up an EKS Auto Mode cluster, which IAM role is essential? EKS cluster role, cluster admin, node group role, or auto role? There you go. Sixth one. What is the primary job of a controller? Delete all pods, control API server, match actual state with the desired state, or build monitoring dashboards? That's the right answer. Yes.
Technically, all of them are doable.
Really? I didn't know that. How do I build dashboards? Okay. Well, most of them were right. So, seventh one. What is a CRD in Kubernetes? Database to just do CRUD operations? A way to define your own API objects? Manage resource cache? Or it's an alternative to kubectl command line interface? CRD stands for custom resource definitions. Which of the following is feature of client Go? Write Kubernetes manifests, analyzing logs data from system, protect the clusters against the bad actors, or establishing a watch connection to the API server? There you go. Purpose of rate limiting in controllers: only allow deployment in a namespace to prevent overloading of the API, to save some energy, or maybe to restart some failed ports. There you go, 100%. Wow, lovely. Everybody's expert now. What does a Kubernetes watch do? Tell the time inside the cluster, establishes a connection to detect resource changes, watches the cluster in chaos, or reads the resource definition and does the automated actions based on it. This is the last one. If someone might want to climb up the ladder, 5 seconds is your chance. All right, that marks me to the end, and let's see the leaderboard. All right, top 3 winners, please stay here after this session and just give me your details, and we'll proceed with 6 months of Code Cloud subscription, where you can learn all the Kubernetes and all the cloud native courses for free. So it's a just gratitude from our end. And that brings me to the end of the session. Bingo. Thank you so much, everyone, for joining in this cold weather and hanging up till 8 p.m. So yeah, thanks a lot. We are open for any feedback or maybe a quick chat, but we might have 10 or 15 more minutes at this venue. So thanks a lot for joining. See you next time. Goodbye.